Let V be a vector space over some field F. Suppose that the dimension of V is n. Let the set V1 up to Vn be a basis for V. If we write these vectors in a sequence, say V1 to Vn, then we call it an ordered basis for V. So in this case, the order in which the basis vectors appear is important. And for example, if UVW is an ordered basis for some vector space that is three-dimensional, then VWU is actually a different ordered basis for the same vector space. So keep this in mind. By fixing an order on the basis elements, we can now represent every vector in V as an n-tuple as follows. Let's take a vector V. Because V1 up to Vn give a basis for V, there exist scalars lambda1 up to lambda n such that V equals lambda1 times V1 plus all the way up to lambda n times Vn. And we're going to define the tuple representation of V with respect to the ordered basis V1 up to Vn as follows. So we denote that by open square bracket V close square bracket subscript the ordered basis. And this is the n-tuple lambda1 up to lambda n. So again, this is the tuple representation of V with respect to the ordered basis V1 up to Vn. Let's now look at an example. Take V to be the vector space of quadratic polynomials in X with real coefficients. And let gamma be this ordered basis here, and omega be this ordered basis here. We're going to find the tuple representations of X with respect to these bases. To find the tuple representation of X with respect to gamma, I first must write X as a linear combination of these vectors. And it's not hard to see that this is given by minus 1 times 1 plus 1 times x plus 1 plus 0 times x squared plus 1. And so the tuple representation of X with respect to gamma is the 3-tuple minus 1, 1, 0. And to find the tuple representation of X with respect to omega, I need to write X as a linear combination of these three vectors. And one can check that this is given by 1 times x minus 1 plus 1/2 times x squared plus 1 plus minus 1/2 times x squared minus 1. And so the tuple representation of X with respect to omega is the 3-tuple 1, 1/2, and minus 1/2. The beauty of these tuple representations of vectors is that we can now work with tuples instead of the actual vectors. And that's because of the following properties. If U and V are vectors from V, and gamma is an ordered basis for V, one can check that the tuple representation of U plus V with respect to gamma is the same as the tuple representation of U plus the tuple representation of V. And if you look at the tuple representation of lambda times U, where lambda is a scalar, is the same as lambda times the tuple representation of U. Finally, some books refer to the tuple representation as the coordinate representation.